remains the ultimate goal that everyone tries to achieve still. This kind of on a second level now, since we can't really control how they behave in a 100% reliable way, actually makes them also really hard to automate. So typically, as you can see here on the left, most LLM settings are human in the loop. There's a human looking at all the individual responses. But if we actually want to use them as building blocks in code, this is not an option. Like we can't have a human in there all the time checking all the responses. So we actually need something better to actually program with them or like build on top of them. And the core thing about this is really this robustness between at the interface of a language model and traditional programs. So a traditional program is always expecting a specific output format, for instance, some structured output, but a language model inherently is based around natural language. So this is kind of the gap that you need to bridge, and we call this kind of interface robustness. This is also one of the main goals of this work. And then lastly, of course, efficiency is still a big topic. LLMs are these huge models running on entire data centers, and every token and every query you can actually avoid is actually a big win in this space. All right, so what's LMQL compared to the standard LLM interaction? LMQL is the idea of a human still writes a program of how we want to interact with LLMs, but the actual interaction happens between a computer and an LLM that kind of go forth and back. Plus the additional detail that in this case, we don't just rely on the LLM to produce some output that we prompt for, but we can actually also force the LLM to respond in a very specific way by applying constraint generation. So this brings us to LMQL to also show some code. Here on the right, you can see a simple LMQL program in the original syntax, also proposed in a PLDI paper. And fundamentally, LMQL is kind of a mix of a traditional programming language and on the other hand, natural language prompting. So you do give a computer instructions in terms of a prompt, but you also have like another layer of control. Most notably in LMQL, you can actually provide these kind of prompt templates, right? On the right, you can see there's that sort of a template with placeholders. And the language model will actually invoke to fill those placeholders, but you can also provide constraints that sort of constrain the model in how it can actually fill those placeholders. So in this case, stopping conditions or length conditions, but you can also do more advanced things like enforcing a regular expression or even grammar-guided decoding. This kind of base framework then allows us to more or less precisely and concisely also express common tasks that are done performed with LLM. So for instance, classification, code generation, or maybe your more advanced building already some kind of autonomous system or agentic system. At the same time, of course, having like a program representation of how people work with an LLM also gives us the opportunity to optimize a lot here, because of it, like to address this need for efficiency, but also because we now have an end-to-end representation, we know what's about to happen, we can kind of schedule things ahead and also avoid unnecessary queries. Specifically in LMQL, this is done by speculative execution a lot. All right, so maybe to, on a high level, classify this, I like to show this picture. What LMQL is kind of this hybrid between traditional coding and LLM prompting. And on the one hand, you have LLMs that are very good at understanding natural language instructions, but typically don't give you any guarantees on the kind of output they will provide on a case-by-case basis. And on the other hand, you have traditional programming, which typically gives you these guarantees, like you can look at the algorithm, you can even derive runtime complexities from it. And also you can derive like correctness attributes from it, but they are not as good at like understanding unstructured data and performing many of the tasks that LLMs are great at. So LMQL kind of is situated at this intersection of the two. So it's kind of the idea of interweaving traditional algorithms and code with language model calls and trying to build this environment to define these kind of hybrid computations that sit between the two worlds. So let me show you a bit of code so you can actually get a feeling of what LMQL looks like and how it works. So LMQL is really a superset of Python. So you can write code like this, which is really just a Python program, right? You can have your variables and do computations on top of them. But the key difference is that in LMQL, you also have an LLM ready all the time. So whenever you have computed something, you can just, like here in line 7, invoke an LLM using this top-level string syntax. And the LLM will actually be able to respond to the kind of values you're currently operating on. So in this case, it looks at the value of program variable C and actually, in this case, provides you a fun fact about this number. So already here we can see in line 9, after doing this, we can actually go seamlessly between traditional algorithmic program and then an LLM that answers some question for us. And then the next level of the more important aspect about this computational model is that this LLM doesn't just disappear, right? So this is not an isolated call, because if I later on in line 12 now ask about, for instance, half of that, clearly referring back to line 7 or what kind of value we just worked with, the LLM will have this in context. So we'll actually understand the kind of past or like history we have and see that previously we talked about number 4, and now this means we have to refer to number 2 now and not 4. So this is already kind of, I mean, this is the basic like programming model. And this already allows us to do a few interesting things. For instance, you can just implement templating now, where you write a program that very precisely puts placeholders in these kind of prompt statements here, where the model is only invoked to fill in those placeholders. And here in this case, this means we can clearly sketch out the kind of response we're looking for. For instance, in this case, we want a structured response in the form of a JSON object. And the LLM will actually only be able to fill in those placeholder variables as declared on the left, leaving us with a much more structured response, which we can then parse or use downstream in some application, in comparison to unconstrained generation, where you would just may even get different kind of output formats depending on the person you ask for instance. So this is templating. And then it gets into constraining, actually. So you can write these programs where you interweave code and prompting, but you can also, and then like the placeholder variables will be completed by the language model. So in this case, C will sort of be the language model will do A plus B for us and produce some value for C. And we can actually inspect this afterwards directly. The problem is a bit now, language models are actually built to interface with humans, so and not with programs or code. So in this case, A plus B, like what is A plus B question mark, will give us the response new line, 2 plus 3 equals 5, which makes sense in sort of a human-focused setting where the language model repeats the question and then gives the response. But in a highly automated setting, this is actually quite difficult, because now we have some long string with new lines in there and different kind of numbers, and it's already not clear what the actual response to this question that we asked is. Like, is it 2, is it 3, is it 5? And typically what you can do in practice, you just come up with some ad hoc strategy of how you can read out the actual response from this value, but this is not ideal because these heuristics don't work always. So the alternative in LMQL is you can actually, when you prompt like this, provide a constraint. And the constraint means whenever the language model is invoked to generate some value, we actually force the language model to pick only from a subset of possible tokens. In this case, for instance, we enforce the language model to only produce numbers. And this can be done because you can actually reduce the vocabulary of the model at inference time to only include numbers. And this means we can directly provide guarantees. So we can be sure that the language model will always produce a number in this case. And also in a more data type, from a data type perspective, we can actually also be sure that we can convert this directly to an integer value, because there's no way there's another kind of value present at runtime, almost establishing some kind of type safety, if you will, in this LLM programming setting. So how do constraints work? How does LMQL enforce those constraints? And for this, it's kind of important to understand a bit how language models generate text. And they do so by generating token by token by token. And at each step, they have like a fixed set of possible next tokens, the so-called vocabulary. And this distribution that they choose this next token from, you can actually limit. Like we can intervene in this decoding process and make sure only tokens are available that we think, according to our constraints, should be available. So for instance, here we can see a simple program on the left. And if we actually decode this and show this kind of as a tree, we can see, okay, the first statement is just hello. So we force the model to produce the word hello. And then we have a placeholder in our program, meaning we let the language model generate some text. So in this case, the language model will generate 2 tokens. And each time at each step, it will actually look at its full distribution, assign each possible next token a score. And then by our decoding scheme, for instance, maybe we are sampling tokens or we just use the most likely one, we will pick one of these tokens and repeat this process. And in this case, the model chooses the world token and then the new line token, and then decides to stop generation for now by indicating this, which is also indicated by pointing to a specific end of sequence token. So this means in our program, we can now extract a value for greeting and then go on in our control flow, again, inserting a static part like how is, and then moving on to the next placeholder. And now again, the language model is invoked. But if we look in our program, we have an additional clause called the where clause, which actually imposes a constraint on this specific placeholder variable. And in this case, we say subject must be in live and or work, meaning we restrict the set of possible tokens to just live or work. And in decoding, this now means we actually don't let the model choose from the full distribution, but we mask distribution such that only those 2 options are available, which means the model again assigns a score to each of those tokens, and we choose whichever scores higher. So in this case, the model is leaning towards live, and we actually can complete the full sequence like this. So I won't have time to go into the full semantics. Like the paper has a nice semantic section of how we go from these constraints to actually masking the next token distribution. One sentence summary is basically we compute a look ahead on the Boolean result of these expressions, and from this we can actually derive a nice token distribution. But yeah, I invite you to take a look at the paper if you really want to go down that rabbit hole. So to show some numbers, these are the numbers from the original paper. So excuse the old model. But what we in the original paper at least already have seen is you can actually boost accuracy slightly, really by just providing constraints that align with what you're looking for. But you can really also reduce token use by a lot, because by constraining the model, by being there every token in a decoding loop, you can actually make sure that no useless tokens are generated and actually save a lot of money this way. I know I'm tight on time, so I will try to give a quick outlook here. Also to like honor some other works in the space and also things that we are doing. So in constraining and grammars, I think this is like a very active area still of how can we make language models behave, how can we make them generate output that's always in a formal language, for instance. And there's 2 important insights, I think, in the space in the past 2 years. So one is this idea that you have to do constraining right, because constraining rightfully, if you think so, like constraining is somewhat of an intervention during decoding, and it's kind of unnatural to the language model because it's not trained that way. Meaning you have to be really careful with how you constrain, and because if you constrain overly restrictive, this can actually have a bad effect on downstream performance. And then another aspect is that you can make this also really fast, which is quite important in high throughput settings, which is typically achieved with pre-computation. So this is kind of also one of our more recent works, and we precisely think about that specifically in grammar decoding. But I just to have a note here, grammar guided decoding is sort of this one direction that derives from here. Another is obviously the question, are grammars the way we should interact? Like grammars are not a direct programming language, or not at least what most people think of when they think of a programming language. What is kind of the programming model of how to interact with LLMs? And I think there's like different needs, especially if things are only semi-structured, maybe because people only have some constraints, but not full-on grammars. And I mean, I think that there's many things happening in the space right now, many really cool projects like AICI or other languages, even like guidance as Glang or these PY, very active areas still, and we're very much looking forward to all the things that are still happening. Yeah, please check out our open source project if you want to. And at that point, I'm very happy to answer any questions.
Thank you, Luca, for a great talk. We are clapping, like if you don't hear us. So
Thank you.
we open the floor for questions. So like in-person attendees, you can raise your hands, and the virtual attendees can raise their virtual hands. And we will like round around with the mic. William?
Hi, thanks for the great talk. 2 questions. First of all, I was curious whether you've explored taking any information about the constraints and actually including that information in the prompt. So basically making the information about the constraints available to the model before it starts the constraint generation process, and whether you think that could have any effect on the quality of the output.
Yeah, so that's definitely what you want to do in practice. And it is very effective because you have to think of constraining as something that's external to the model, right? So the model will not know what's coming. And if you suddenly force it to produce just numbers, this can actually have a really bad effect if it doesn't expect this to happen. So typically in practice, what I should suggest is like you want the constraining for the guarantees, but you also kind of want to prompt so the model is kind of aware of what's about to happen and during decoding and sort of is primed in the right way. Because if you constrain too strictly and the model is not aware, you can end up in really bad spots of the probability distribution where everything is basically uniform and only noise that you're sampling from because the model like didn't really expect it to go down that route.
Cool, thanks. And the second question is, do you think that there might be any like extensions or like particular aspects of the system that would work differently in a setting where the constraint generation that you're doing is for the purpose of like function calls or tool use? Because with tool use, you can end up, for example, in situations where like the correctness of like some kind of API call or similar that the function that like the model is issuing depends both on its sort of like syntactic correctness, but also on maybe upholding some sort of like deeper semantic and invariance in the API that it's interacting with. So I was wondering if you've given any thought to what it would look like to enforce those, or maybe like backtrack if like a call fails.
Yeah, totally. It's a very interesting direction for sure, and we're also monitoring this closely. I think like there's 2 ways to approach this. I think one is like for now, LMQL is and also all the constraint generation space is really about syntactic constraints, right? And as you say, like sometimes when you call a function, there are much more semantic, maybe even specifications that you want to satisfy. So one way to solve this is kind of you could superimpose sort of a semantic layer on top of the syntactic layer, sort of allowing users to specify logic constraints in logic, and then sort of propagating this back to syntactic constraints. We haven't done this yet. I also imagine this to be somewhat limited. Like I don't think you can enforce everything greedily, and then this sort of goes to what you mentioned. Secondly, is backtracking is kind of the only way. Backtracking, or what I've also seen to be quite successful is just giving the model an error message, and the model can actually recover itself. Like you wouldn't backtrack actually in terms of the tokens you generate, because this means typically that the language model will just make the same mistake again. But you want sort of this failed attempt in the context for the model to try something different. And that's very has also been shown to be quite effective. So I think both options are possible. And yeah, we recently actually also looked more into this idea of enforcing more high level and semantic constraints as well.
Yeah, thanks. Yeah, and I guess like including the error messages in the prompt sort of gets back to your answer to the first question as well. In that like you want to like encode as much useful like context for the model to operate with as possible. So it does.
Yeah, you want it to be aware and to have guarantees, like sort of the best of both worlds for sure. Yeah.
Yeah, makes sense. Thank you.
Thank you.
Cool. I think Saman had, or Armando.
Hey, this is Armando. Great work.
Hey.
So I have a question. So when you're doing this constrained decoding to make sure that the output satisfies some constraint, sometimes the way you write the prompt can make a big difference in terms of how likely those outputs are. And so I guess this is two questions. The first one is, does this make a difference at all? Does tweaking the prompt so that the outputs that you want or that satisfy the constraints become more likely, does that actually make a difference or help, for example, with performance? And number two, if it does, do you have some kind of feedback that you can provide to the user that says, hey, the outputs that you want are actually like really, really low probability. Maybe you want to change how you wrote your prompt to make them more likely.
Yeah, for sure. So part one, that's definitely the case. Like you want to have examples or a prompt that makes what you're forcing eventually very likely under the model distribution. Otherwise, it's kind of this issue that you will go into these dark places of the probability distribution where the model kind of sees just a very high perplexity sequence of tokens that it can't really deal with. And this also means every next token it generates becomes much lower quality because it's sort of a bad setup. And the worst cases of this I have seen is, for instance, when you provide demonstrations in a very specific format and then force a slightly different format. So for instance, what you want to do to actually validate that your prompt is kind of in line with what you're constraining for is you want to push your demonstrations through the same constraints and make sure your constraints would validate on the demonstrations you provide. So it kind of is a natural progression also to the model. And this happens actually much more easily than you would think because of the incredibly messy nature of tokenization of language models. Sometimes it's enough to like tokenize your demonstrations differently than what you're forcing and constraining, and then things really go downhill from there. And then to the second part of your question, we do have in our decoders, for instance, warnings when probabilities go very, very low, basically uniform token distributions. And then you can actually see, okay, I'm only seeing randomly sampled tokens, and even there's an error message or warning message informing you that something went wrong. But I would say sort of the process of debugging this is actually still quite difficult. And yeah, I mean, beyond this, we don't provide any tooling, but I think it would actually be quite interesting to work on. Yeah.
Cool. Thanks.
Thank you.
Great. Let's thank Luca again